Good morning, students. Today we are going to discuss probably the last topic from the chapter 10, Mechanical Properties of Fluid. Now the topic which we are going to discuss is capillarity. Now all of you heard, I think, what is capillary tube. Probably you have used also. The straw which you used in drinking soft drink can also be defined as a capillary tube. Now, in science, what is capillarity and what is capillary tube? That part we are going to discuss. So it says that a glass tube of very fine bore throughout the length of the tube is called capillary tube. It means throughout the length, the bore should be uniform. Okay, the hollowness should be uniform throughout the length of the tube. Then that tube can be defined as your capillary tube. The phenomenon of rise or fall of liquids in a capillary tube is called capillarity. Okay, capillarity means what? The rise or fall of liquid inside the capillary tube. And the capillary tube is nothing but a uniform bore throughout the length of the tube. Any glass tube. Here it says glass. It may be of plastic also. Just like in cold drinks, we used straw. That one is also some kind of capillary tube you can consider. Now, how do the liquid rises inside the capillary tube? That part we are going to discuss today. Now you see, when you put a capillary tube inside a liquid, what will happen? The liquid rises up to certain extent above the free surface of the liquid which is available in the container. So here you see in figure 1, we have inserted a capillary tube in the container containing liquid. So what will happen? The liquid rises up to certain extent and after that it stops. Okay, why does it stops after attaining certain height? That part we are going to discuss. So number 1 diagram, now you see the final diagram, not final diagram. If you want to relate this diagram, this is your number 1 and the diagram, the bottom one. You see this thing happen when you put the capillary tube inside a liquid container. So if you see the top view, you will see that the free surface is curved. Definitely it is due to the surface tension. Now if you see from the top view, you will see that there is an hemisphere and below that hemisphere there is a liquid, and also the liquid raises certain height which we define as h. The height which we have defined is nothing but is your h. Now you see in this figure we know the free surface is not a straight, rather it is curved. So here we are considering water, so the curved surface is your concave. Now at the edge of the wall there is a surface tension force which makes an angle theta with the wall of the container. So you can see that that theta is the angle of contact if you draw the tangent to the curved surface. Now tensional force X, now if you take the component, you will get T cos theta parallel to the wall and T sin theta perpendicular to the wall. Now this side also, in both sides, T cos theta will be there and T sin theta will be there. T sin theta balances each other and T cos theta is responsible for taking the liquid up inside the capillary tube. Now you see this T cos theta acts throughout the circumference of the hemisphere, you can say T cos theta. Now T cos theta pulls the free surface of the liquid up, and when the liquid moves up, definitely a weight will act vertically downward. So this T cos theta corresponds to a certain force, as we have defined. Tension is nothing but the force per unit length. So T cos theta with the circumference of the hemisphere, that is your 2 pi r, that is nothing but the total force acts on the free surface of the liquid which is available inside the capillary tube. Now due to this parameter 2 pi r T cos theta, the liquid rises up to certain extent. Now when the liquid rises up, there will also weight acts vertically downward. So as it moves up, T cos theta 2 pi r balances the weight of the liquid that rises inside the capillary tube. Now when this happens, the liquid stops rising further. Okay, so these are certain parameter you have to consider. Tensional force acts tangent to the curved surface at the walls of the container. Theta is the angle of contact, so it has two components. One is T sin theta, another one is T cos theta. T cos theta acts across the circumference of the hemisphere if you look it from the top, and this force correspond to T cos theta balances the weight which acts vertically downward. So to get the weight of the liquid that moves inside the capillary tube, what you have to do, you have to calculate the volume of the liquid that rises. Now you see, the volume of the liquid that rises is nothing but the volume of the cylinder of height h, that is your pi r square h, which you have given pi r square h plus. Now you see, if you consider the cylinder whose whose height is your small r, then it is your pi r square r minus the hemisphere. Hemisphere is your volume is your 4 by 3 pi r cube. So what you have to do, half into 4 by 3 pi r cube. So pi r square r is the volume of the cylinder of height r, and minus volume of the hemisphere gives you the volume of the liquid available below the curved surface but above the height h. So total volume comes out to be your pi r square h plus pi r cube minus 2 by 3 pi r cube. So pi r square h, if you take the LCM, 3 pi r cube minus 2 pi r cube, pi r square h plus 1 by 3 pi r cube. So if you take common, pi r square h plus r by 3. So this is the volume of the liquid that rises inside the capillary tube, and after that it stops further rising. There will be no further rise in liquid after attaining height this much, or after attaining the volume this much, and the height is your h plus r by 3. Now this one balances the this weight corresponds to the volume is nothing but is your this formula, W equal to mg. If you consider rho is the density of the liquid, then volume into density gives you the mass, and g multiply gives you the weight. This weight acts vertically downward. Now this weight balances the component or balances the force corresponds to the T cos theta. So T cos theta 2 pi r, this gives you the total force in upward direction, and weight gives you the total force in downward direction. Now in equilibrium, what will happen? Pi r square h plus r by 3 rho g equal to T cos theta 2 pi r. So on simplification you will get h plus r by 3 to T cos theta by r rho g. Now if h is very greater than r, so that should be h equal to 2t cos theta by r rho g, and this formula possibly known as ascent formula. So sometime in exam it is asked to define the expression for the rise of liquid inside the capillary tube, and in that case you have to define h equal to 2t cos theta by r rho g. So you see this diagram, I have drawn few diagrams separately so that it's very easy to understand. So liquid rises inside the capillary tube after a certain extent, after that it does not rises. Now the free surface inside the capillary tube is not in straight, rather it is concave, because we are considering the liquid as a water. Now if you see the top view, you will see that there is an hemisphere and of radius smaller, which is nothing but the radius of the capillary tube. Now T cos theta x throughout the circumference of the hemisphere, and this T cos theta pulls the liquid up, that's why liquid rises, and but it does not rises beyond a certain extent, because that force is balanced by the weight of the liquid that rises inside the capillary tube. So under that condition the liquid stops rising. Now the rise of liquid is inversely proportional to the radius. If radius is less, height will be more. Okay, that's our generalized formula, h proportional to 1 by r if other parameter remains constant. Now the numerical which we are trying using this formula, please see. The sap in trees, which consist mainly of water, rises in a system of capillaries of radius 2.5 into 10 to the minus 5 meter. The surface tension of sap is 7.28 into 10 to the minus 2 Newton per meter, and angle of contact is 0 degree. Calculate the maximum height up to which the sap can rise in the tree. So you see what are the parameters given. Radius is given r 2.5 into 10 to the minus 5 meter. Tension is given 7.28 into 10 to the minus 2 Newton per meter, and angle of contact theta equals 0 degree, and density of water is nothing but is 10 to the 3 kg per meter cube, and h we have to define. So we have to use directly this formula, h equal to 2t cos theta by r rho g. 2t is your 7.28 into 10 to the minus 2, cos 0 is your 1, 2.5 radius 2.5 into 10 to the minus 5, and rho is your 10 to the power 3, and g is your 9.8. So ultimately we are getting 0.59 meter. So the height of the liquid that rises is 0.59 meter, or you can consider 0.6 meter also, 60 meter approximately. So you try a few numericals, and also in offline class we'll try the numericals from this chapter. So please go through. Probably in offline class next day, means from 18 onwards, we are going to start thermal expansion and thermodynamics. So please go through, and also we'll try numericals from the chapter which is in your syllabus. Please check out and try to understand. Thank you.